Hello, everyone. I think we can begin on time and people can enter at any time. Okay.
Yep.
请当马队。Dear colleagues, both present in the conference room at Hainan University and joining us online, welcome to today's special academic lecture. Today, we have the privilege of hosting a renowned figure in the field of physics and mathematics, Professor Gates, who will deliver a fascinating talk titled Chen-Xiong Wu, Mandate Observer of Nature's Secrets. Professor Gates, a prominent theoretical physicist at the University of Maryland, holds esteemed positions, including the Clark Leadership Chair in Science, the University System Region Professor, and the John Stoll Professor of Physics. His groundbreaking work at the intersection of physics and mathematics has garnered him numerous accolades, including the prestigious National Medal of Science in 2013, the highest recognition for scientists in the United States. Additionally, Professor Gates also served as president of the American Physical Society in 2021. In his presentation, Professor Gates will delve into the profound discoveries made by Professor Chen-Xiong Wu during the years of 1950 to 1957, shedding light on nature's deeper secrets and the observable effect of its peculiarity. Through his insightful discussion, Professor Gates will provide us with a unique perspective on Professor Chen-Xiong Wu's remarkable contribution to the field of physics. During the lecture, if you have any question, please wait until the lecture is over. I invite you all to join me in welcoming Professor Gates as we embark on this enlightening journey together. Thank you.
Well, I hope everyone can hear me. Can someone give an indication?
Yes.
Loud and clear.
Yes.
Yes.
Thank you very much. Well, first of all, I would be remiss if I did not thank all of those responsible for this fantastic invitation. Chen-Xiong Wu has been a hero of mine for decades, and so to be asked to speak about her work is a great honor for me. So let's get started. This is the talk is not going to be highly technical because I wanted to capture the spirit of what I think are just two remarkable achievements. And so let's get started. This talk that I'm going to give is an upgraded version of a presentation I made several years ago when the 110th birthday anniversary celebration of Chen-Xiong Wu was actually carried out here in the United States, sponsored by the American Physical Society, the Chinese Physical Society, and also one of the a university whose name escapes me right now. And on that occasion, I was asked to speak about her, and I was so pleased to have the second invitation certainly just increases my pleasure. So what is it that I just find so fascinating about her? Well, her science. So let's talk about that. This talk, as I said, is probably at the level of a popular level talk. But it seems like all of you are physicists, so I beg your indulgence as we go through these things. We have a clock here. This clock is going to take us down to scales of size. Each mark is a power of 10 as we look at it. And so here we are at 10 to the minus 5, the scales of blood cells. These are cartoon animations of newly emerging blood cells from bone marrow. We can get down to like 10 to the minus 9 strands of DNA, also the realm of nanotechnology and nanoscience, which is a bursting part of technology development these days. And of course, if we continue down one order of magnitude below that, we get to the scale of the atomic realm, and namely a cartoon here of an atom with its electron clouds spread out around it. So in this, at this level, chemistry emerges, because essentially the rules of chemistry are really determined by the orbitals, which are the shapes of the electron clouds around the nucleus. And here is the table of elements. The table of elements actually has a very interesting history. It comes to us from Mendeleev, And when Mendeleev first wrote the table of elements, it was much smaller, and there were missing elements. And so he actually used this paradigm to predict the missing elements, which were later found. And of course, the table has expanded very greatly since then. Here are the shapes of those electron clouds. I think essentially all of us are physicists on this talk. And so we certainly have the experience of deriving the hydrogenic wave functions, which we can see written in the upper corner of this slide. It involves Laguerre polynomials and circle harmonics, and then certain normalization factors. But this mathematical formula, when you turn it into graphs, gives us the shape of these clouds. And then in turn, the shape of these clouds then determine how elements interact with each other, bonding, etc. But let's continue our journey, because this was all at 10 to the minus 10, which is about the size of the atom. So continuing, we can get to smaller and smaller scales. We'll penetrate the clouds of electrons. And now we're entering the realm of nuclear physics. So here we have a cartoon illustration of an helium atom with 2 protons and 2 neutrons. And we're going a little bit deeper in this cartoon because we see there's something inside of the protons and neutrons. And of course, these are supposed to be evocative of the quarks that exist in the interior of nuclear matter. Of course, the nucleus, as we physicists well know, is not a static object. It's, in fact, one of the first major developments in understanding nuclear physics was analogizing it to a liquid drop. And so we have this liquid drop model of the nucleus, which actually helped to lead to the discovery of the von Weizsäcker mass formula. And so these models of the nucleus that we often teach about don't capture the dynamical structure, which is actually there. Since we're in this realm, we know that all of the elementary particles, the quarks, the electrons, have spin. And in fact, all the particles, even the Higgs particle and the force carriers, have spin. But what distinguishes the electron and the quarks and ultimately the neutrons and protons is they have spins of a half. Mathematically, we can write a formula for the magnitude of the spin. And again, if you recall your quantum mechanics course, this formula will, of course, spring to mind. So there's even more motion. Now, of course, quantum mechanical spin is not the classical spin that are illustrated by these cartoons at the bottom. But for people who are not physicists, this is supposed to be evocative to get people to think about the properties of spin. One of the strange things about spin, quantum mechanically, if we were talking about a spinning object in the real world, in our three-dimensional world, we can write down a spin vector. That vector can point in any direction. But if you're doing a quantum mechanical measurement, something very interesting emerges. And this was first seen in the Stern-Gerlach experiments. Namely, that if you try to measure a spin quantum mechanically, what you find is it's true that the spin is a vector, but you can only measure one of its 3 components, definitely. And typically, those of us who take a course in quantum mechanics will tell you, well, just pick the spin along the z-axis. You pick the spin along the z-axis, then the spin can take on the values of either +1/2 or -1/2 h bar. Now, since the other components of the spin of expectation value x direction and the expectation of y direction are indefinite, what we can say is that the spin vector, if you imagine that the electron is at the center of these 2 spheres that you're looking at, and we orient the z-axis along the vertical, then what we can say is that the spin vector actually points to 2 lines of latitude, if you think about the spheres being the Earth. They're both about 54.7 degrees north and south, and the spins point somewhere along there. The spins don't actually rotate as shown in these images. This is just showing you different choices that the spin vector can take, consistent with having a spin 1/2 degree of freedom along the z-axis. But of course, those of us who study quantum field theory, which is the basic mathematical language for describing the experiments and the results that we've obtained in both the atomic and nuclear realms know that other particles also spin. In fact, this quantity J that we introduced earlier quantifies that spin. Now, not all particles spin, it turned out, because the Higgs boson is spin zero. The Higgs boson, of course, is a very, very special object. It's the only fundamental spin zero particle we've ever discovered as a species. Now, it's possible that there will be other spin zero particles out there. I have spent my career thinking about the ideas of supersymmetry. And if supersymmetry is an accurate description of nature, then you might expect that there will be at least 4 other spin zero fundamental bosons out there. Now, a lot of people, of course, like to say supersymmetry is dead. So let me give you a little bit of history here. I actually wrote MIT's first thesis on supersymmetry in 1977. And at the time, no one else at MIT knew anything about supersymmetry. So I've watched the field from its birth, at least here in the United States. Because of my observations of supersymmetry, and first, it is an incredibly mathematically powerful set of ideas, which has contributed theoretically. In fact, just last week, I saw a beautiful talk given by Hitoshi Murayama, where by using the ideas of supersymmetry, and in particular, an idea called the conformal compensator, which is a piece of mathematics that Warren Siegel and I introduced to the physics literature in 1978. But by using this piece of math magic, if you call it that, Hitoshi is able to find hints about how low energy QCD emerges, which, for example, with insights into the condensation of the lowest bosonic states, namely the pions. So he has a beautiful set of arguments, and anyone who wants to see what supersymmetry is actually useful for in the real world, I would say go look at those papers by Hitoshi. You may find them quite astounding. So because of my relationship with supersymmetry and that's been my singular interest in my career, I've done some other things phenomenologically. I've talked about an idea that what would happen if the lowest lying supersymmetric particle has color, because after all, in a supersymmetrical theory, there are quarks and there's quarks. So suppose the mass spectra was such that the quarks were the lightest supersymmetric particles. Then, because of color, if these things hadronize, then because color, you would have a hard time finding these objects. And so I've tried to think broadly about how nature could treat supersymmetry. And because of this, in 2005, in Physics Today, you can find an article entitled, "Is Superstring Theory Phenomenologically Viable?" And in this article, I make the argument that if we were not going to find supersymmetry when the LHC turned on. This is shortly before the first scientific run. And in this same work, I did a back of the envelope calculation, looking at questions about thresholds and deviations of G-2, and I concluded that if we believe that there will be avatars for supersymmetry, they would be seen in precision experiments first, like G-2, or other divergences, for example, the running of coupling constants in QCD and QFT, that those are the first signs of supersymmetry. And then finally, on the basis of these things, I basically, you can call it either I was lucky or else maybe I do have some insight, but I stated in the article that 30 TeV seemed like a reasonable number to me about where you might be able to find supersymmetry. So I wasn't surprised when the LHC didn't find it in the first scientific run, nor the second scientific run. And so if my back of the envelope calculation and intuition is correct, we may now just be beginning to see the kinds of avatars that I expected would show up as the first signs of supersymmetry. Most of you in this audience may have been following the G-2 results from the muon, which seem like they're trying to tell us that there are additional particles out there. And so this is the kind of signal and the use of precision in high energy, which I was arguing for in 2005 and 2006, would be a path forward for discovering supersymmetry. So contrary to the meme that supersymmetry is dead, I believe, in fact, it's very much alive, and it's very much like Mark Twain that said that rumors of his death are greatly exaggerated. I think that ultimately will turn out to be the case for supersymmetry. But now let's get back to our main subject.
Are the slides frozen?
No, they should be.
Oh, okay, got
now.
it. No problem.
Okay, I just froze them while I took that diversion into discussing why supersymmetry isn't quite dead yet.
Okay.
And also why supersymmetry is what has apparently shown usefulness in trying to understand some of the non-perturbative effects in QCD.
Got it.
So back to our main story, as I said, other particles spin. The photon has a spin of 1, and I just showed its helicity states with a cartoon. But now we come to quantum entanglement. So for this, quantum entanglement is a situation that occurs when this definition, by the way, was taken from Wikipedia, which I think is just as good as any other definition that you could find on the market, occurs when a duet of particles are generated, interact, or share spatial proximity in such a way that the quantum states of each particle in the group cannot be described independently of the state of the other particles, including when the particles are separated by large distances. So here, again, because I'm speaking to an audience of physicists, let me try to try something out on you. Maybe you can try it on your students. When we learn quantum mechanics, one of our first exercises is the particle in the infinite square well. That's an easy problem. You can calculate the eigenstates, the eigenfunctions, the eigenvalues, and the wave functions, the normalized wave functions. Now, if you put two particles in an infinite square well and try to find the wave functions, you can do that by assuming that it's a product of one particle wave functions. But then something very interesting happens if the particles are indistinguishable and if they're fermions. Because if you try to write down that wave function, it turns out you have to have an anti-symmetric combination of the two single particle wave functions. And so therefore, just having that second particle in an infinite square well determines that there's a 0 in the middle of the square well in terms of the probability of finding either electron. And so in some sense, this is a primitive example of entanglement, because here you can see a physical implication just because of the symmetries, and the symmetries here kind of force an entanglement in that example. So that's the simplest way I know how to explain entanglement to say freshman or sophomore level physics students. And as this quote continues, measurements of physical properties such as position, momentum, spin, and polarization performed on entangled particles in some case are found to be perfectly correlated. And we're going to come to that shortly. So let me continue. There's a process called spontaneous parametric down conversion, which can be used to split ordinary photons into pairs of type 2 photons that have mutually correlated perpendicular polarization vectors. And so here we see a real world example, not in the simple case of the two particles in the square well, but a real world example where entanglement can occur. So this brings us to the Einstein-Podolsky-Rosen paradox. I have a cartoon on the left here where we're talking about two particles with spin. And you'll notice this correlation when the particle in the back is pointed perfectly vertically front, the particle in the lower is pointed to the back. And so this is a cartoon example of what it means to find a correlation between objects that are quantum mechanically entangled and you separate them. So this brings us to the first, what I call first mandated observation by Professor Wu. So this paper, which was published in 1950 by C.S. Wu and Irving Shaknov, is a paper studying the angular correlation of scattering annihilation. Excuse me. Sorry, scattering annihilation radiation. And it's, so let's go through this because it's a very interesting and simple experiment to understand. To pull this off, however, is amazing. And Professor Wu with her student Shaknov were not the only people trying to perform this experiment in the period of 1947, 1948, 49. Shortly, about 14 years after the EPR paradox was first realized, people started to try to see if they could find violations in laboratory experiments. Professor Wu and her collaborator were the first ones to do it and nail it down exactly correctly. So let's go through it. So her experiment that makes this observation possible is that it involves the weak interaction. Now, the experiment itself does not illuminate properties of the weak interaction. Her second, as I call, mandate experiment, are going to do that. But in this first experiment, it begins by taking an accelerator and using it to create a beam of copper 65, if I remember correctly, which is a highly unstable nucleus. It is so unstable that the weak interaction, which this cartoon is trying to capture in the right here, takes the nucleus and breaks it apart. And essentially, it's a very efficient beta decay. So here's a more, I'm sorry, it was copper 64. Here's a chart that shows us what happens. After you create this highly unstable nucleus, it decays. But what's interesting about the nucleus is that you get beta decay, normal beta decay, and you get anti-beta decay, namely electrons and positrons are both copiously produced in the decay of this nucleus. Now, having having the electron and its antiparticle in a very close proximity then leads to the following result. The electrons and positrons are antiparticles, and therefore they can collide and completely annihilate each other, giving a 100% conversion of Einstein's E equals MC squared equation. And in the process, to preserve all the appropriate quantum numbers, what you have to have coming out are two gamma particles, not a single one. And so there you have these two different channels for watching electrons and positrons decay, and the resulting photons produced, shown on the right-hand side of each of these Feynman diagrams. So what Professor Wu and her collaborator Shaknov did was to measure the correlations of the photons that are coming out of this experiment, and they set up a very clever apparatus. They took the measurements at angles of 0, 90, 180, and 270, and calculated the correlators. And what they found was that there was, in terms of experimental error, they found a correlation that was consistent with the ideas that come from the EPR experiment. And so this is Professor Wu's first amazing, well, she did many amazing, but to me, this is earth-shattering, amazing result about the structure of our universe and pinning down nature's secret. As you all know, Einstein, throughout his life, was never a fan of quantum mechanics, which is, of course, interesting because I'm sure many of you, like me, have taught courses on quantum mechanics, and we observed that one of the strongest early impetuses for quantum mechanics was actually Einstein's work on the photoelectric effect, which shows the quantization of the energy carried off by the electrons from the emission. And so even though it's perhaps paradoxical that Einstein actually gave an early push to quantum mechanics and its acceptance in the physics community, as we all know from the history, at least in the history that I've read, He never fully accepted the idea. And the EPR paradox was actually stated as a way to prove that quantum mechanics, in fact, was not correct, that there had to be something else. And the most popular approach is something called hidden variables. So Professor Wu's work says basically says no hidden variables, folks. We're going to have to stick with the quantum mechanics that came to us from the 20s and 30s, starting with Bohr and then working its way through Schrodinger and Heisenberg. That is an accurate description of how our universe works, even though it is weird. So that's the spooky action at a distance, is that when things are quantum mechanically entangled, when they are even separated, they somehow continue to have the attributes of both particles, even when they're separated in ways that common sense says should not be possible. This eventually leads to a Nobel Prize. Alan Aspect, John Clauser, and Anton Zeilinger in 1922, I'm sorry, 2000, in 2022 were awarded their Nobel Prizes, essentially on the foundation that was started by Professor Wu. So that's the end of the first part of my presentation on mandated observations. I'd now like to go to the second part. The second part is the one that's more widely known, and it has to do with what we physicists call non-conservation of parity. So let's go through that one. Here's a picture of Dr. Wu, Professor Wu, in the laboratory. And what I have to the left is a simple Feynman diagram showing the quark content of a neutron and a proton, beta decay acting on the neutron so that the neutron quark turns into an up quark, causing a proton to appear on the other side. And then the beta decay of the W particle emitted decays into an electron and an anti-neutrino. Now, of course, the process that we have illustrated by the cartoon Feynman diagram isn't what you can actually do in the laboratory, but what you can do is, again, work with unstable nuclei. And so if we take, for example, carbon-60, we can watch a transition where carbon-60 turns into nickel, an electron, an antineutrino, and two gammas, all determined by the conservations of energy and momentum and the usual laws that we believe accurately describe physics. So part of Professor Wu's genius was being one of the world's most adept nuclear physicists at conducting very difficult experiments. And in the first part of my talk, I talked about the fact that her work is actually the first that actually experimentally observes entanglement. Here, we're going to continue the story to non-conservation of parity. So again, since this is an audience of mostly physicists, perhaps, I'm sure you're aware that in the realm of the nucleus, there are three fundamental forces that we have to worry about. There's the strong nuclear force, illustrated on the far left by the symbol S. Here, basically, I'm talking about quantum chromodynamics. In the middle, we have the weak force, weak interaction, again, illustrated by the cartoon of a neutron decaying into a proton, electron, and antineutrino. And then finally, to the right, we have the good old electromagnetic force. So these are the forces that are relevant if we're going to understand the physics of nuclei. In particular, the gravitational force is not relevant. And it's not to say that it doesn't exist, but it's not relevant to certainly at the energies at which we're able to observe the nucleus. And so to the first approximation, I, like everyone else who teaches a course on nuclear physics, we simply neglect gravity because it's not going to give us observable things. So it's a moot point about what one is talking about. However, as we talk about nuclear physics, and right now I'm actually, well, this is my second year teaching a course called the Manhattan Project. And of course, if you're going to understand the Manhattan Project and atomic bombs in a physics class, you're going to talk about nuclear physics. And so I've had the great pleasure of reviewing my nuclear physics that I learned as a graduate student. This is a very familiar curve to lots and lots of physicists. What we see to the left is the energy per unit nucleon as you start to add more and more nucleons to a nucleus. Now, what's interesting, of course, is that the curve, as we see, goes up and up until it gets to iron, and then it turns over. And this curve is one of the most, to my mind, is one of the most beautiful things I've ever seen in physics, because it explains why stars evolve as they do. A star burning principally hydrogen runs out of hydrogen and it burns helium, but that's going to a more stable state. In fact, the great law that you're trying to go to a minimum drives stars through their life cycle until they get to iron. But there are many more elements above iron. And the rather interesting thing is some of these elements are necessary for our biological systems to work in the way that supports life here on Earth. And so the way that these, I'm sorry, so there's noise. The way that these elements on the top part of this curve are created is through supernovae. That is, stars have to explode and they create these really large nuclei. Those nuclei tend to be unstable and decay naturally. And so this curve, like I said, is one of the most beautiful things I know in science. It explains why stars evolve the way they do over here. And then from here, the fact that these elements are there requires stars to explode. And Carl Sagan, back in 1980, made a statement which I had never heard before. I'm not sure if he's the originator of it, but he said, we're all made of star stuff. And by that, scientifically, he was referring to the fact that the elements up here in this part of the curve are elements that were cooked by supernovae, and that those elements can be found in our body, which is, like I said, it's just sort of an amazing thing to contemplate. Here's one of those supermassive nuclei that you find in this region. And so, as I said, this curve, this binding energy per nucleon curve is one of the most, I think, one of the most interesting things in all of science. We, on one hand, understand stellar evolution from this side. From this side, we understand why these elements are like 10, I believe, here, why these elements are naturally unstable. And it all binds together. And the liquid drop model is part of this story. So this, the development of this clear picture of nuclear physics has some superheroes, if we can call them that. There's the Nobel Prize that was given to Enrico Fermi in 1938. Enrico Fermi is a person who first wrote down what used to be called the first version of the universal interactions for universal weak interaction terms in Lagrangians. It's a product of two currents. We see the currents here, and these are the quantum wave functions. And of course, Fermi was perhaps, so again, since I've been teaching this course on nuclear physics, I've had a chance to revisit Fermi's role in the early development of nuclear theory. And of course, Fermi is an amazing physicist. The work he does, both in the laboratory and the work that I'm showing you here, which is theoretical. Many people said that he's the last complete physicist, because it's very rare that you find physicists who have been able to contribute at the level of both experimental and theoretical physics as Fermi. These two young men, a very young picture of Professor Yang and Professor Li, and the Nobel Prize that was awarded in 1957. They resolved the so-called theta tau puzzle, which there were these two sets of what seem to be two sets of decays, and one parity, in one of them, it looks like parity is acting differently than the other. So these were things were initially thought to be two particles, but as we will see in a moment, they're not. There are other people who did work in this area, and two of them were Richard Feynman and Murray Gell-Mann. In my life, in 1980, I was a postdoc at Caltech. I think Dave may have actually been there then. We'll have to go into that. But I was a postdoc actually in the group of Gell-Mann and Feynman, and they had what was called V minus A theory. And that's, again, something that Professor Wu actually worked on. So now we come to what I call mandate number 2 observation. So we're going to first take a diversion into a little bit of solar orbital dynamics. If you were to look down on the solar system from a northerly direction, you would note that all the planets revolve around the sun in a counterclockwise direction, as you see in this cartoon. If you look at Earth and most of its neighboring planets, you will also see that they also rotate in a counterclockwise manner. And so the sun, for us, rises in the east and sets in the west. However, as James Donahue at NASA has this nice diagram that you can find at YouTube, shows that planets have different obliquity. That is, planets, the axis of rotation for planets can point in many different directions relative to the plane of the rotations of all the planets in the solar system. So in particular, our Earth's axis is tilted around 23 degrees. But look at Venus. Venus is actually over at 177. That's almost 180, which means that it's almost upside down. But also, we note that Pluto has a very a very oblique angle for its for the axis of rotation. Now, all of this is relevant. For example, we can imagine in our mind's eye or in a science fiction story going to Venus. And if you go to Venus, you find something very interesting. The sun actually rises in the west and sets in the east. Now, again, think about a science fiction story where some astronauts go to Venus. You know, we know that that the environment there is terribly inhospitable to human to almost any biological life that we can think of. Although there, for those of you who may, could everyone mute? Is it possible? Because I keep getting sound. Thank you. As I was about to say, we know that in reality, the environment on Venus seems extraordinarily inhospitable to biological life. Although, again, if you watch what's going on in science broadly, you will know that some astrobiologists are actually starting to give, and in particular, there's work at MIT, are starting to give some plausibility arguments about how life might be able to survive in the atmosphere. Is it going to work? I don't know, but it's something to keep an eye on. So, but if you went to Venus in our science fiction story, I bet you wouldn't expect for gravity to work any different than it does here on Earth. So, mandate number 2 observation. We earlier talked about the fact that in the realm of nuclear physics, the only forces that are relevant to things that we can observe are the weak nuclear force, the electromagnetic force, and the strong force. Strong force for the binding of nuclei in those nucleons that we showed in the curve of energy per nucleon. Weak interaction because it drives the beta decay of neutrons into protons, electrons, and antineutrinos. We're fortunate that we live in a universe where the neutron is about 1,831 times more massive than an electron, but that the proton is only 1,830, and that slight mass difference then allows beta decay to take place. So these are 3 of the forces. And so you might have the expectation that the spin of a nuclear particle does not have any impact on the nuclear forces that it feels. And so again, this time in the experiment, Professor Wu is going to be actually probing the structure of the weak interactions itself, not as some secondary process that is initiated by the weak interaction, but studying the weak interaction properties itself. Again, there's a paper that we can find in the Physical Review Journal's archives, published in 1957. And in this paper, which also is related to the work of Li and Yang, which was responsible for their receiving the Nobel Prize, as well as another group that was experimentally testing periodic conservation and beta decay. It's also published in 57. So first of all, if we look at the mathematics that comes to us from Fermi, we can draw a Feynman diagram that looks like this. Remember, Fermi interaction was a product of two currents. Each current is bilinear in field operator, so it's actually a four-point interaction that he's describing. Professor Wu's observation is so powerful that ultimately it's going to lead us with some elaboration of a couple of decades to the modern version of the weak interactions. So let's remind ourselves quickly of all the standard model particles, which we see here. And so what happened? Well, in her paper, let's go back to the paper. Here, in the paper, she and her collaborators were able to show that the nuclear force, if you look at correlations between spins, I'm sorry, correlations actually between helicities of particles, you could show that a particle with spin up is not treated by the weak nuclear force in the same way that a particle with spin down. Using the analogy that I built up earlier for any young people who might be in the audience, I argued that it would be very strange if we lived in a universe where if a planet is rotating, such as Earth, the force of gravity would be different than it would be on Venus. This is the analog of what Dr. Wu and her collaborators found. This is something stunning to find a force that depends on the state of spin for the particle that's subject to the force. And yet, this is what we've led to. And as I said, ultimately, this is the basis, one of the bases for why we ultimately get to today's standard model, where the 4-point interaction by Fermi is actually the limit of two three-point functions, and the limit where the exchange momentum goes to zero, you then recover Fermi's 4-point interaction. And so Professor Wu's contribution at this point is astounding at a level that verges on almost indescribable. So she's a hero to me for other reasons. She was obviously a great scientist. And let me say something about her academic lineage, something I learned at a meeting with Professor Feng a few years ago. Professor Wu's principal instructor in nuclear physics was a gentleman who was the student of Madame Curie. So Professor Wu is the academic granddaughter of Madame Curie. Madame Curie, as you know, was also an extraordinarily extraordinarily accomplished physicist. And here her academic granddaughter turns out also to be an extraordinarily accomplished physicist. So after the non-conservation of parity was observed in the laboratory, it led to Li and Yang becoming recipients of the Nobel Prize. But many of us have long recognized that Nobel Prizes aren't given for mathematics. They're given for a piece of theoretical physics for which there is experimental and observational support. If you look at the non-conservation of parity, the observational and experimental support for that assertion comes from Professor Wu and her work. And so many of us have felt for a long time that she should have become a recipient of the Nobel Prize. Her work here on the non-conservation of parity will stand the test of time as one of the greatest discoveries ever made in physics. And she had comments of this. I've read about her. She was always a gracious person, independent of this inappropriate treatment that many of us feel she was subject to. And I don't have to tell you, or it's obvious she's a woman, and the forces against women doing science have always been very substantial, and it was true in her time, and to some degree it continues to be true now. And yet, in spite of that, she achieved at this extraordinary level. And so one of the things she said, that the main stumbling block in the way of any progress is, and always has been, unimpeachable tradition. So if you have a tradition that keeps women out of science, her life provides an example of the opportunity cost that would occur by preventing her in science. And it's likely true for other women. She also said, men have always dominated the field of science and technology, and look at what an environmental mess we are in. This comment is both jocular and serious. And so she made the statement, which was something I've known about for a long time. And then finally, Claire Luce Booth, a famous playwright, said that when Dr. Wu knocked out that principle of parity, she established the principle of parity between men and women. And I would make a subtext, at least in science. So Dr. Wu is not just a scientist of extraordinary ability. She's a person who overcame challenges. And that's something that I admire in any person, but certainly someone who's a scientist in the science I love, in physics, and at the level at which she accomplished it. Let me close by pointing out that she has a legacy. There is a satellite called Mikius, which in 2017 was one of the most practical demonstrations of the technology of entanglement being deployed in the real world. So there's this article that came out, and I put the Zoom link in for anybody who wishes to look at it. And then finally, this is something that's still going on today. The work by the scientists associated with Mikius continues. And so they're actually untangling the technological applications of using entanglement for progress in communications, and quantum communications in particular. And this rests firmly on the foundation of the work in the first mandated observation of Professor Wu. And so I think we all can give her a round of applause for having contributed so much to science, as well as to our understanding of the sociology of science. So thank you for listening. I will end now and take questions.
Thank you for this wonderful talk. If anyone have question, you can put it out in the conference room. Anyone have question? Okay.
So hello, Professor Gies. So I have a question about the supersymmetry, and yeah,
Okay, that's funny because
yeah, I think maybe you are the most famous expert on supersymmetry, and so supersymmetry is fantastic both in idea and mathematical structure, but the experimental test is still some problem there. So I'd like to know, so if finally the experiment can't find supersymmetry, so what should we do with the supersymmetry, or what the supersymmetry can do in that scenario? Thank you.
sure. Well, first of all, that scenario, and from my perspective, was very predictable. There was a hysteria about supersymmetry. And as I said, I wrote MIT's first thesis on the subject. So I was very aware of how unlikely it was that it would be discovered at the LHC. So what I tell people is the following. When I was a graduate student, supersymmetry was, to me, the most interesting and exciting theoretical idea that I saw being debated. But let me also tell you that when I was a graduate student, I had only two aspirations in science as possible avenues of study. The first one was general relativity and gravity, and the second one was particle physics. And I chose particle physics. And why did I choose particle physics? Because that's where the data was. And that's what science is ultimately all about. And so for a young person these days coming along, I would apply the same metric that I applied. Where is the data that is going to drive the progress of our science? Now, I'm convinced, by the way, that at some point supersymmetry will be found, but it has the reasons I think are not the ones that most people talk about. Instead, as I have long argued, that the most likely reason supersymmetry is going to play a role in our universe has to do with the stability of the quantum vacuum. I think that's why supersymmetry is there. And so, like I said, I'm not particularly worried that that it wasn't found at the first round of second rounds of scientific experiments at the LHC. If I was a young person, would I have that same willingness to study this? Well, I told you what my metric was when I was young, so you can answer that question.
Thank you. Any questions?
Hello, Dr. Gates, can you hear me?
Yes, I can.
Oh, hi. Thank you for your nice talk. I have a question regarding the Dr. Wu, CS Wu. She did a lot contribution to physics, but she was not recognized, like by giving Nobel Prize. And according to your comment, mainly because she was a lady, or what is the real reason she did not receive the Nobel Prize?
I thank you for the question. I can only surmise, like everyone else, the fact that she was a unusual young woman. And in our discipline, like I said, to some degree now, it is still the case that people who are underrepresented minorities are not expected, nor are they recognized for contributions that are made by such individuals. And it's not that there's some evil force at work. One of the things I find amusing about scientists, and especially physicists, is people like to say, oh, there's no sociology in what we do. But of course, everything done by humans has sociology. So to make such a statement on the face of it is, to me, ludicrous. So yes, it's probably something to do with the fact that she was a woman. And your colleagues, if you're, like I say, if you're from an underrepresented group, you find your colleagues are skeptical and often not willing to give you the benefit of the doubt. I've seen this many times in my own career, by the way, so this is no surprise.
Okay. Thank you.
You're welcome.
Jim, I like to ask a question, something that I always wonder, because I've heard it.
Dachuan, can I point out that Bill Phillips has his hand up?
Oh, sorry. Bill Phillips, please, Bill, go ahead.
No, go ahead. I'll ask my question.
No, you go ahead. You trump me.
Okay. When the story of parody is told, Madame Wu figures very prominently in that story, along with Li and Yang. But when the story of entanglement is told, she does not. Do you have any insight into why that is?
Bill, that's a great question, and I must admit, I do not know. I myself only became aware of this about 4 or 5 years ago, and I would defer to my colleague Dachuan Fang, because we were both at the conference, and Lars Brink, I don't know if folks know who Lars Brink was. He unfortunately is deceased, but Lars Brink, who was part of the selection committee for the Nobel Prize, is the person who brought to this celebration, remember I said there was a 110-year birthday anniversary celebration of Professor Wu. And Lars Brink was one of the speakers at the program. And he's the person on the program who pointed this curious fact out, that the first experimental observation of entanglement was carried out by Professor Wu in the late 40s and early 50s. I have no idea why this has been absent from the story for so long.
May I say a few words about that?
Please.
About 5 years ago, I was at the home of Professor Yang in Tsinghua University in Beijing. And for some reason, we talked about physics. And I asked Professor Yang, what did he think about entanglement? He turned to me and said, do you know who was the first person who experimentally verified entanglement? I said, I have absolutely no idea. So it was Madame Wu, Wu Jianxiong, as he said it. But he didn't, he said, I published somewhere in long time ago. You can find it. It took me a couple years to find it. And when we organized that meeting 2 years ago, Lars was the one who actually went in and dig deep into that paper and talked about it in his talk. If anyone wants to get Lars's PowerPoint, I'll be happy to send it to him or her. I have actually another question about parity. Jim, you're an expert in this area. When parity is discovered, what impact does it have on physics at the beginning of the Big Bang? And does it have any implications to us today because there was a parity non-conservation, that we are able to see something that is due to that?
Yeah, so Dachuan, let me give you asked one question, but because I believe in quantum mechanics, I'm going to give you two answers. The first thing that one wonders, so in elementary particle physics, there's this great theorem called CPT, charge parity and time reversal, and all of the, I don't know of any field theory model in which CPT doesn't hold. On the other hand, we know that parity is not conserved. We also know that charge conservation is not. And so my first answer to this question is the fact that there is an apparent asymmetry in our universe between particles and antiparticles we can't, we can't find the antiparticles as a sort of the shorthand story. So maybe somehow this is connected to the non-conservation of parity. I don't know. The other thing that I would give as a possible answer to your question is that I have over the years consistently heard some people in biophysics argue that the non-conservation of parity at the elementary particle physics level may have something to do with the asymmetry in chemical structures. So, if you look at chemical structures, they can have handedness right and left-handed. And so we only, if I remember my history correctly, or my biology, we only process, I think it is left-handed sugars, but there are right-handed sugars that biologically we don't process. So the argument is somehow, and no one has, in my reading, given a ironclad argument about how parity non-conservation at the level of fundamental particles winds up as asymmetry in biology and chemistry, but that argument has been made. That's the only other thing I can say. I see Jingbo has her hand up.
Yeah, just want to follow up on the entanglement question. And I should have read Madam Wu's paper carefully. I meant to ever since last year, but I haven't. So this is quite naive, possibly comments. So in the world around us, there are lots of different kind of correlation. There are classical correlation, there are quantum correlation, which termed as entanglement. So yeah, from my very really a naive kind of comment, entanglement can be confirmed essentially, especially nowadays, using John Bell's inequality. And that inequality was established around 1970s. So Madam Wu's work, earlier work on the correlation, I'm 100% confident, sure. She did observe a correlation between the two gamma photons emitted from this annihilation. I just wonder whether she was able to establish correlations beyond the classical type of correlation. For example, I often have students come to me and say, Jingbo, I put two objects in a box, and one is white, one is black. And I don't look at them. Of course, I don't know which one is black and which one is white. And I took one far, far away, maybe even go to the moon. If I don't look at it, it's 50-50 of the possibility of that object being black or white. But as soon as I look at it, if it's black, I know immediately the other one is white. And that's the entanglement. I said, no, that's not. That's classical correlation. So the only way to establish this correlation is beyond classically allowed kind of relationship. As far as I know, it's only through Bell's inequality. So you establish by assuming there is hidden variable, that is the object without looking, it's still, it doesn't matter whether you look or not look at it, it's black. So that hidden variable will lead to equality, a relationship. But so if you have quantum, so just yeah, one more. If you have quantum correlation, that's what we now call entanglement, and it will valid. Yeah, will not satisfy that equality. So I'm just wondering whether Madam Wu's work can be restudied and pull out the data. I assume she would measure polarization 45 degrees, 90 degrees, and so on. Yeah, okay, that's all I want to say. Thank you.
Let me just say one thing in response, Jingbo. Let's see, what was I thinking? Can
I say something?
Sure, this is Naftali.
First of all, my comment about the fact that Madame Wu didn't get the Nobel Prize, I think is not right. She should have. But she got many prestigious prizes later. compensate. For example, the Wolf Prize, which I was present in Israel. That's a very, very prestigious prize. And about entanglement, I would like to ask you here, was there given a Nobel Prize to someone?
Yes.
Yes, but for specifically for defining it or finding it. I mean, because it is all over. I mean, any correlation, so many, that is entanglement. So if someone noticed it, the first is probably the paper of, I'm not sure, by Einstein, Rosen, Podolsky. And Einstein got a prize, but not
Yeah, the prize
actually
was
for
awarded
that.
in
2 years ago. Zeilinger, Cronin, and I forget the third one, but it was, as you were saying, it was always for, I think, Bell's inequality measurements. And that was going to be my question as well for the Wu's experiment. Like, was it considered measurement of entanglement at the time? Sorry.
So I am not an expert in this area. So all I can do is read literature like the rest of my colleagues. And by the way, Seda, I'm glad you spoke up because I saw your hand and I was going to call you, but Naftali he started talking, so I went to him first.
Yeah,
Great talk. Thank you very much. Yeah.
There are few in the Nobel Prize. Usually it's fine, but usually there are some mysterious things. For example, why didn't Kabibo get the Nobel Prize, but the other two got it? And he is a man.
Good point, Naftali. Good point.
Yeah.
Okay.
It happens. But I hope in the future there's also probably a question of this thing with Lisa Meitner, which she should have gotten.
Oh yes, well that's another case, of course. I think everyone, maybe everyone's not aware, but the Watson-Crick unraveling of the DNA.
Speak up if you can.
Oh, I'm sorry. I said I hope everyone on the Zoom is aware that Watson and Crick, who unraveled the story of the double helix, actually used no, I'm sorry. I'm thinking of another scientist. You said Lisa Meitner. So you're talking about nuclear physics. I'm actually talking about DNA. I'm sorry. So these you can call them mistakes or whatever. They're part of being human. We humans make errors. That's why we have error bars in physics.
Well, since we talk so much about Nobel Prizes, we have a Nobel laureate here, Bill Phillips. Would he ask the question?
Oh yes, Bill, can you weigh in on this, Bill?
You have to unmute.
Unmute it.
Right. Sorry. As Jingbo said, in order for quantum entanglement to be shown, you need to show a violation of Bell's inequalities.
Right.
And I mean, this is the first I've heard of this experiment by Madame Wu, so I don't have any idea whether her data shows a violation of Bell's inequalities. As Jingbo suggested, one could look at the data. And of course, as she also mentioned, you would need to have orientations of the polarizers that are different for the two different detected photons in order to see a violation of Bell's inequality. So for example, the violations that were seen by Clauser and Aspe and Zeilinger involved looking at correlations when the polarizers were not in the same orientation. If the polarizers are in the same orientation, it's just as Jimbo suggested, it's just like white ball, black ball. It's it looks completely classical. And so we would have to see whether those kinds of polarization orientations existed in Madame Wu's earlier experiment. I think it would be really interesting to look at that.
Yes, I must admit, I never, when I was invited to give this presentation, I never thought that it might be an occasion to go back and study Professor Wu's results to see whether there is a violation of Bell's inequality there. I mean, that's just fascinating. And given the quality of her work, those records probably are somewhere that can be investigated.
Well, I'm thinking if somebody wanted to look at the original data for some of my old experiments, it might not be very easy, but maybe I'm guessing that she was better than I was at organizing things. One final thing, as long as we're bemoaning the lack of recognition for women with Nobel Prizes, you were mentioning the Rosalind Franklin situation. Another important one is Jocelyn Bell should have had the Nobel Prize for the discovery of pulsars, and that was a great travesty. And it could have easily been done because you can only give the Nobel Prize to 3 people, and they only gave it to 2 that year. So she could have easily been.
Yeah, sure.
And well, as you say, we are imperfect.
Error bars.
Yeah, it's a great pity John Bell passed away so early, so young. Otherwise, I'm sure he would have been.
Yes, I agree.
Well, Dashwan, you're actually, as far as I can tell, the person who controls this. So what is your direction, sir?
I'd like to know whether there are any more questions.
We have one question in the conference room.
Okay, please, go ahead.
没有开。
Hello, Professor Gates. I have one question. We know that we can calculate the binding energy of the atom or molecule from the first principle. My question is, can we calculate the nuclear binding energy from the first principle now?
So first of all, let's make sure that when you say we can do this for atomics, I assume that you're using what is it called? Density, local density approximation, Tam-Shan type equations. Is that what you're talking about when you say we can do it from first principles? Hello?
Yes. Well, for example, we can calculate the binding energy of the atom from the Schrödinger equation, or
Well, first of all, for atomic systems, there's something else called if I remember correctly, Tam-Shan equations, which are local density approximation. It's not just a Schrödinger equation. It's sort of Schrödinger equation plus something that looks a little bit like statistical mechanics. It's a collective effect. So but to answer your question, QCD may be getting closer to that, but since I'm not a nuclear physicist, I don't know, and would defer to the judgment of anyone else on the call who might be a nuclear physicist. There's a message in the chat from Jingbo about quantum computation. Jingbo,
Yeah,
your hand up is up, Jingbo.
Yeah, I just want to say thanks to Phil. Actually, yesterday I was giving a lecture on introduction to quantum computing, and this is what I used as one of the statement from you. And we are in the era of a second quantum revolution, and quantum computing it's coming. And Phil was commenting some time ago, quantum computing is a radical departure in information technology, more fundamentally different. If we compare currently what we have to Abacus, so this is going to be a huge quantum leap into the future. I just want to say thank you. It's so nice to see you here.
Well, thank you. You're very kind.
Hello, Professor Gates. Thank you for your talk. I have a question. As we know, when Professor T.D. Lee and Xin Yang published their paper, the author is Lee and Yang. But when we talk the Nobel Prize, we also, just as in your talk, we also talk Professor Yang and Lee. Why we change the order for their
authorship. Is there any evidence to show that we have to change the order? This is my question. Thank you.
I would defer this question to Bill Phillips, who, as far as I can tell, is the only one among us who's close to the Nobel Committee or has been touched by them. Maybe he knows the answer. I don't know the answer to that question.
No, I certainly don't know the answer either. It might be in the records. The records of the deliberations of the Nobel Committee are made public 50 years afterwards, and I think it's been long enough that one could find those records.
Anyone have questions?
I only have a rumor answer to the question why 50 years after the Nobel Prize, the discussion among the committee is still not out there. So I think we'll have to wait a little longer. By the way, I also put in the chat room the reference to Wu and Sheknov's paper in Physical Review. It's Physical Review 77-1, page 136.
Well, I don't see any more hands, Dashwan.
Yep, I think we have not exhausted the questions, but maybe we have tired everyone out.
Yes.
So people from Hainan University, what should we do next now?
Well, may I have a comment?
Yes.
Sure, please.
Okay, so I've been watching the list of names, and there are so many friends of mine, some of long duration, like Ling Chao, I see, and Michael Dine, I see, and even more recent friends like Alexis Dixon, and then some of my current students are actually in here. So I just want to thank everyone for taking this time out of a Friday evening to come and hear a physics lecture. Most people on Friday evenings go to parties or bars, so I don't quite know what to make of the fact that people show up for a physics lecture. But thank you.
Thank you. I think if there is no questions, we can close the section because I think the time is not so early for Professor Gates, right?
It's only 9 o'clock.
Okay. Thank you, Professor Gates, and thank you for everyone.
Thank you, Jim.
Professor Gates.
You're welcome. Bye-bye.
Bye-bye.